So I think we're ready to continue with the afternoon's talks. So we have 4 more talks to get through. And first out is Daniele Bielli, who's going to tell us how useful auxiliary fields are.
Does it work? Yeah, okay. So good afternoon, everybody. I'd like to start by thanking the organizers for putting up this next conference and for the possibility to speak. It's really a pleasure to be here. So I'm going to talk about a little bit of work that we have been doing the last year or so with Chris Ferco, that you know very well by now. And I'm going to be talking about some very closely connected topics compared to what they talked about this morning, and also with Michele Galli, Liam Smith, and Gabriele Mazzucchelli. So let me just start with a very brief and little bit of motivation. So we know that the increasingly important role played by integrability in the last decades has sort of triggered the search for more and more examples of integrable theories, because they are very interesting, very nice. And there's been a sort of various techniques which developed to try to understand how to explore this landscape of integrable theories. And in the context of 2D sigma models, this has been motivated by ADS-CFT and string theory to a good extent. And the technique, sort of one of the techniques that people have adopted is this deformation technique that I think all of you know here. So the idea of starting with some theory that we understand to a certain extent and trying to make it more complicated, deforming it in some controlled way, so that it preserves some properties as we like integrability. And so I will be focusing on this class of deformations, which Christian also introduced earlier on today, these auxiliary field sigma models. And I would like to sort of try to highlight some nice features and some possible drawbacks of this approach. And I would like to do it by discussing 2 applications that we have been working on. So the first is the non-abelian dualization of TT-bar-like deformed PCMs, and the second is the construction of higher spin conserved currents and their associated deformations. So I will just very briefly recap quickly the auxiliary field sigma model in one slide, then discuss about these 2 applications, and then wrap up. Okay, so very briefly again, Christian already did all the job and introduced this deformation, but just to make sure that we're on the same page. So this deformation was introduced last year by Chris and Liam, taking inspiration from some 4-dimensional even observation formalism for principal current models. And so basically the way these are engineered is by the introduction of some auxiliary fields, this V plus and V minus that you see here in this deformed action. And basically they are the way it works is that you flip the sign of this standard principal current model, which is usually a minus, in this case it's a plus, and you couple trivially this auxiliary fields to the Mara-Cartan current. And then all the sort of magic in a way is this in this object, this E of nu2, which is called an interaction function, which is some unspecified function of one variable at this stage, this variable nu2 that you see here, defined in terms of auxiliary fields only in this specific combination. So how is this a deformation? As also Christian said, this is the equation of motion for the auxiliary field. This is the equation in the middle. I don't know if the pointer is visible, but anyway, this equation of motion, which has the dot on the equal sign, which denotes an equality which holds true when this equation is verified, is on shell, relates the v's to the j's and to the interaction function, to the derivatives. So this makes clear that whenever we choose a trivial interaction function, vanishing 1, basically the v's are just proportional to the j's, and if we substitute them back into the action, we recover the original principal current model. This equation is very important, very crucial, because it implies this sort of so-called fundamental commutator identity, which is basically just a statement that on shell for the auxiliary fields, you can trade commutators of V's and J's with commutators of V's. And this is very important because, as again, Chris will say this morning, allows basically to show that integrability is preserved for these models. Indeed, you can, if you compute the equations of motion for the fundamental fields of the principal current model, the G's, you will find some sort of modified conservation equation. There is this frac J here on the left-hand side, which is defined here in terms of J and the auxiliaries. And there is on the right-hand side some commutator terms, which make this equation not a conservation. But if you go on shell for the auxiliary fields, you use this relation, the fundamental commutator identity, and this turns out to be a conservation equation. which can be encoded in the flatness of a deformed wax, which is the one written here. So here we can already see like a feature, which I will also come back to later, which is that basically there is a splitting of the conserved current. In the standard principal current model, we have the J, which is both conserved and flat on shell. Here we have now two currents, J and frag J, which are related in terms of the auxiliaries, via the auxiliaries. And one of them is flat, but not conserved, while the other one is conserved, but not flat on shell. So we have this splitting that I will again come back on later. So, okay, given this framework, one more important part. If one integrates out the why these models are interesting, okay, well, of course, first of all, they preserve variability, as we said. And if you integrate out the auxiliary fields for some choice of interaction function, non-trivial, what happens is that you are fundamentally inducing deformations by functions of the stress tensor, and which deformation you're inducing depends on the choice of interaction function. So with this in mind, there is one first application that I want to discuss. As I say, it's to the T-duality. But first to discuss this, let me start by sort of very briefly recalling what I mean by T-duality, what I have in mind. I am a bit old-fashioned, so I have in mind this sort of a standard old procedure by Quevedo and Delossa from 1992, which basically is an algorithmic procedure to derive the dual model. And for principal current model, which have this big isometry group, GL across GR, this algorithm says that if we want to dualize, for example, along the full left sector of the isometers, or equivalently well to the with respect to the right, we can simply introduce a gauge field which gauges the left sector of the isometries, this omega plus here by minimal coupling. Then we can modify the action by introducing a new term, which is a Lagrange multiplier terms. Lagrange multipliers of the algebra values as match the gauge field. And this term enforces the flatness of the gauge field and ensures that we can go back in the procedure if we want. And the third step is exploiting this gauge freedom to basically get rid of the G, setting it to the identity so that we are basically left only with omega and Lagrange multipliers. And at this point, the last step of the procedure consists in integrating out these gauge fields, and so by solving these equations of motion that you see here on the last bullet point. So if we solve this equation, we substitute back into the model, we obtain a new model, a new sigma model, which is called the T-dual, in which the Lagrange multipliers now play the role of dual coordinates, this sigma models. Okay, so now a question that one might be interested in asking, at least I was interested in asking, is, okay, we have this nice procedure, well-defined, people have studied this to some good extent. Okay, can we now try to apply this procedure to some more complicated classes of models, and specifically to TT bar and root TT bar deformed principal current models? It's sort of for me, it was sort of interesting and natural to wonder, because these actions are known, are the first two lines here for TT bar and root TT bar. They were found, they were computed a few years ago. And I thought, okay, maybe it would be interesting to see what happens in this models if we perform the T-duality. So okay, if you try to do this, it's sort of how to say, sort of visible that you can more or less easily do the first three steps. So you can certainly introduce the gauge field, you can modify the action by introducing the Lagrange multiplier term, and you can gauge fix G to the identity. So for example, if you do it in a root TT bar case, you get this equation here, this Lagrangian here. So it all seems to go smoothly so far. The problems come when we have to do the last step. So when we have to integrate out these gauge fields and really get the T-dual model. So now if we compute the equations of motion for the gauge fields, which we need to solve for omega plus and omega minus, we end up with this last line here, this equation of motion, which is quite more complicated than the one that we saw on the previous slide. Of course, this recovers the other one when we send gamma to 0, because this recovers the undeformed PCM. But this is a quite nonlinear equation, which depends on omega plus and omega minus. First of all, couples them, and also there is this square root. So it's at least for me, it was a very hard equation to solve. But okay, so there is this new formalism, this very nice way of sort of recasting the TT bar and root TT bar deformations for principal current models. So can we do this with this new formalism? And okay, well, I showed already the action for this deformed principal current models. It's sort of easy to repeat again, also for this model, the first three steps, and this is the action that you obtained. And you see that now the sort of good feature of having this auxiliary field in this case is that now all the non-linearities of the deformation are encoded, secretly encoded in this interaction function, which only depends on the auxiliary fields. So this basically allows you to compute the equation of motion and to find something which is very simple. It's basically as simple or as complicated, if you want, as in the principal current model, the form 1. And basically all the information about the auxiliaries is on the right-hand side. It's this shift, the Lagrange multipliers. So this, in this sense, the auxiliary fields makes this operation somehow quite more complicated with respect to what I showed you on the previous slide. And in fact, this is not the end of the story, because once...
Are your auxiliaries now transforming under the gauge algebra?
No, the auxiliaries transform are assumed to transform like the J's. So at this point, I've gauge fixed the gauge fixed G to 1, and I have to the auxiliaries are transformed like Noir-Cartan form. So in this case, no, wait, I see what you mean. Yes, I think they should transform. Yes, like the gauge field. Yes. Yeah, I think they should, because in the dual model, there should still be the invariance under the right transformations. So when you obtain it, you should be able to recover this also for the deformed case.
So it is linearly transformed under your group. The transforms linearly transformed.
The Cartan, the Mario-Cartan form J transforms like with respect to the right action transforms adjointly, right?
No.
So the auxiliaries are assumed to transform adjointly as well.
That's right.
Yeah, yeah. And indeed, if you go back to the where is it? If you go back to the equation of motion for the auxiliaries, I mean, the equation of motion shell tells you that the auxiliaries are precisely proportional to the Mario-Cartan current, except that you have extra terms, and you have to sort of perturbatively try to substitute this equation, and they transform like the J. Then we'll go back to this point actually at the end. Okay, so there is more indeed, as I was saying. Once you have understood that you can perform the dualization, perform the deformation, and then dualize, you can also wonder, can I do the reverse set of operations? Can I first dualize and then perform the deformation? And it's not straightforward, but it turns out that you can actually do these two operations. You can study like what happens in the two cases, and you can wonder, are these two theories the same? And it turns out that the two theories are indeed the same up to some field rule definitions, which act on the auxiliaries. And also another interesting point is that there exists a canonical transformation, which was found out by Yolanda in 1995, which relates the initial and dual model in the undeformed case. And also what turns out to be the case is that this canonical transformation remains unchanged for all the models in this class of deformations. Okay, so this is more or less what I wanted to tell you about this first application. So now there is the second one, which is application to the higher spin deformations. So okay, just to briefly recall some results from the literature which motivate this. So in this paper, Osmero and Logic, it has been shown that for 2D integral quantum field theories, the existence of a higher spin conserved currents allows you to basically construct a certain local operator, which is well-defined, well-behaved, and the OP is well-behaved, and up to total derivatives. And this operator can be used to deform the original theory, and it has the nice feature that preserves integrability upon introducing it, modifying the theory. And also this operator, for n equal to 2, when j is equal to the stress tensor, basically reduces to the known TT bar deformation operator. So from this point of view, it sort of makes sense to ask, okay, we have a sort of a formats which produces TT bar-like deformations of the theory, and we have this sort of generalization of the TT bar, something which reduces TT bar. Can we sort of modify these formulas to generate something which at the classical level resembles this type of deformations, or sort of classical Smirnov homological-like deformations? And it turns out that it is somewhat possible to do this, at least this is the first analysis, and it's not so complicated. So basically one can extend the definition of the variable, this nu2, which is defined, as I said, in the trace of v plus square, v minus square. So one can extend this to some higher k by taking trace of v plus to the k, v minus to the k, and promote the interaction function to depend not only on nu2, but also on other nus, 3 and 4 and higher. And basically it turns out that if by picking a certain specific choice of interaction function, the one there on the left, proportional to lambda n mu n, where lambda is some deformation parameter, what happens is that if we integrate out the auxiliaries at this point and we do it to linear order in the deformation parameter, we are indeed inducing this type of deformation, which are of the form of the current that I showed in the previous slide, with this j plus n, j minus n, which are basically the n power of this Marquardt current. And this construction that was mentioned in the first slide, and also this p-duality story, this sort of extend also to this larger set of interaction function, and interoperability is to preserve. Okay, but then there is another question that one may ask. Okay, so this holds true for principal current models, leading order in the deformation parameter. Can we do it? Can we do something better? Does this extend in some way? And okay, well, first of all, this deformation has been sort of extended to other classes of sigma models. We have been working out symmetric and symmetric spaces, Jan Baxter, a few classes, and David Austin, Axel Kleischmidt, and Mattia Cesaro worked out the higher ZN cosets. And something that at some point we noted, and that this now connects to what I was mentioning in the first slide, is that the equation of motion for all these models can be sort of written in a sort of a single way, in a unique way, sort of. In terms of this, okay, so the first equation is a sort of a conservation equation for a certain current B, which is written in terms of another current A and the auxiliaries. And you already may notice here a similarity with the first slide, where basically B is the frac J and A is the J, little j. Then there is a middle equation, which is this auxiliary field equation of motion. And then there is the last equation, which is sort of a flatness condition for A. And here we see that if we set the interaction function to 0, delta, which is the relation of the interaction function, is 0, and so A is minus B. And if we substitute this back into B, we recover that B and A are the same. So we have this mechanism in all these models in which basically we are splitting a current which is conserved and flat on shell in terms of two currents which are related through the auxiliary fields. So and this structure is a sort of a very useful, turns out to be very useful, because basically allows to obtain this relation that you see here on the last line. And this relation turns out to be crucial if we want to study these higher spin deformations. This relates derivatives of the trace of n power of the auxiliaries with derivatives of the delta, the variation of the interaction function. And these objects here appear when we compute the higher spin currents. So using this relation, basically, the auxiliary sort of gives you like a, how to say, a recipe, well, not a recipe, like give you a technique to try to compute this higher spin local conserved currents, which is the first point, and then also to characterize the interaction function which drive Smirnov homological black flows. And because basically these two conditions translate into require this identity. So basically you can write down a system of equations and study these two conditions. And this can interestingly, nicely can be done beyond unique order in the deformation parameter lambda n. And And this is since this structure of equation that I showed holds for all these classes of sigma models that we took into account. These two properties can be studied for all of them, independently of their detailed structure. And also another nice property is that this can be studied by using a simple ansatz for the currents, which are only based on chiral traces. And this is a nice feature because basically allows you to avoid a little bit of a headache in constructing this ansatz for the currents, because you can just blindly take chiral traces, and then the auxiliary field equation of motion will automatically take care of non-chiral contributions, because they will basically relate v plus minus to a certain order to v minus plus at the next order. And so when you recursively substitute the equations of motion in your expression, you will basically mix all possible type of traces. And this type of analysis also reveals another sort of interesting property, which is that these variables nu2, nu3, nu_n that I mentioned earlier, which sort of extend naturally this ansatz nu2, the interaction function. In fact, if you want to actually construct these higher spin currents and this interaction function, you need to actually to enlarge even further the ansatz by breaking down this nu2, nu3 into their sort of building blocks, which are these nu plus minus 2, nu plus minus 3 that you see down here, which are these sort of non-Lorentz invariant parts. Okay, so this is roughly speaking the advantages of the auxiliaries. Now, just to conclude, I wanted to mention some possible limitations that we have noticed. So this approach that I just showed for the construction of these higher spin currents seems to sort of gives you like a prescription to do the calculation. So in principle, you know how to do it, but it is not clear yet how to systematically do it for like arbitrary n. Because basically the set of equations that you need to deal with becomes larger and larger and more complicated. So in principle, it gives you a recipe, but practically speaking, it's not clear how to do it. We managed to do it for some subclasses of deformations and for some subclasses, and also obtaining explicit expressions. Everything is nice until you have to actually integrate out the auxiliary fields to obtain something. And when you do this, well, you sort of do it perturbatively, as I was saying earlier. And this is one type of, for example, this is an example of the form Lagrangian that we obtain for this special subclass of deformations, in which this O and K, these basically are just some objects which, depending on how you pick them, you basically are specifying one of these classes of sigma models that I was mentioning earlier. And so this is the same structure which holds for all of the classes. Okay, so just to briefly summarize and conclude, okay, I've sort of tried to describe this this class of sigma models, principal chiral model formed by auxiliary fields, in which if you introduce auxiliary fields, you're basically can preserve integrability and induce the formation by functional stress tensor forming an infinite family. And this some nice property in the study of interplay with T-duality. And also extend to higher spin, other classes of sigma models in a sort of a useful partly unified frame, which still needs to be fully understood. And there is many open questions that, of course, are turn out in this setting, as also Christian was mentioning earlier. For example, I would be interested in seeing explicit application of the IDS context, which was, at least from my side, the original motivation for studying this interplay of this deformation with T-duality, and then possible extension beyond sigma model, which is not clear yet how one could possibly achieve this. And then this characterization of these Lorentz breaking formations and so on, so on. Like framing within the higher dimensional perspective seems to be also very interesting and promising direction, which sort of has been partially addressed by Fukushima and Yoshida last year in a paper in which they proposed a deformation of the Fordician Simons by auxiliary fields, which reduces into dimension to the auxiliary field principal chiral model. And of course, the quantum level question remains, understanding which interaction function would remain consistent. Okay, so
you. So while the next speaker gets set up, do we have any questions for Daniela?
Thank you for the lovely talk. In your one of your initial slides, so you said the model is integrable regardless of which interaction function involving. I think it was V plus, one of V plus or V minus. I don't remember which.
The interaction function.
Yeah.
Interaction function is a
V2. Yes.
new two. Yes.
V2.
Yeah.
Oh, I see. Oh, I thought. Okay. Yes. Actually, I still have a question. Does this have to be ultra local in V2? Does it have derivatives?
Okay, so when you show that this when you want to show that the Poisson brackets of the components of the Lux take the ultralocal Meyer form, basically a key feature is that the auxiliary fields actually do not appear at all in this structure. This is sort of the whole magic of the formulation. So basically, you don't have to worry too much about these auxiliaries because they don't appear. So the ultralocal Meyer structure which appears is exactly the same as the one that would appear for the principal chiral model, and all these all the properties of the principal chiral model remain sort of on the form remain the same.
I guess I agree, but now I realize that you can't have derivatives of the V's.
Yeah, you don't include derivatives of the V's.
Yeah, okay.
Yeah.
Then I've answered my question.
In the example you gave for the principal chiral model, the action of the group is, let's say, one-sided, so you don't have any fixed points in the.
Yeah.
I was wondering if, since you mentioned the old work of Quevedo and the Lausa, in there, one of the applications is on the Schwarzschild black hole.
Yeah, okay.
Where actually you have the S2 instead of S3. And there you need to be more careful with the gauge fixing and all that. I was wondering if the formalism applies in these kind of cases.
Yeah, okay, it's a very, very nice question. I don't know because we never tried to work this out, but I think it would be very, very interesting. Yeah, there might be some chances that it works, but I think it would be very, very non-trivial. Indeed, also in the underform setting, understanding how to gauge fix the degrees of freedom, it's not always super easy. So I think in this case, probably one would have to gauge fix also some of the auxiliary fields. So it might be not immediately straightforward. Maybe if you know how to gauge fix the underform degrees of freedom, this will sort of suggest you how to gauge fix also the auxiliary fields, but it would be very interesting to look at.
Okay, one last brief question.
In this framework, is it easy to go ahead and calculate the renormalization effect on E, like the one loop calculation?
Oh, and the honest question is, I don't know. I don't think it's that easy. I don't think we have ever thought about this yet. We think, okay, of course, it will be very important to compute like consistency of these models at the quantum level, but we've never really thought about this. There might be some approaches that one could try to take, some other sort of type of quantization techniques. For example, maybe exploiting this higher dimensional, these many symmetries, these higher spin symmetries. Maybe it could be possible to exploit some techniques coming from, for example, from W algebras or.
Oh no, I'm talking about something much more naive.
Yeah.
No,
but I think we
expand around the classical vacuum and calculate the one loop.
Probably not renormalizable, right? I was asking yesterday. I was asking yesterday, and so it's not renormalizable. So you have to add much more counter terms, and probably it will not not even make sense to calculate this way.
Isn't it a canonical transformation?
Yeah, this is like
Shouldn't it be renormalizable?
No, but it's classical, you know. There is a difference between classical and canonical. I'm not sure. But, I mean, I think it does not imply, you know, that having a canonical transformation does not imply
That's from experience. If the original model, you know, the RG flow equations.
Yes.
And there is another model which is classically canonical equivalent, then the anti-flow equations remain the same.
But this works for the sigma model. I agree.
For
But
the
this is not a sigma model right here. So there is much more Because I mean, the sigma model is of course renormalizable on its own. So I mean, you just have to add an R phi term and then it's renormalizable. But these things.
I think we have to postpone further
Yes,
discussion
okay.
for the coffee break because we have another talk before the break. So I think we should thank Daniela again.